One of the most impactful pieces of engineering is the technology of movies. They've shaped every aspect of our lives. Today, of course, they're created digitally, but I celebrate here the stunning engineering that gave life to movies, the technology that tricked the mind into seeing a moving image. Film came in many sizes, from the giant 70mm, popular in the 1960s for epics like Lawrence of Arabia, to 35mm used for most feature films, to 16mm for schools, and even 8mm used by home enthusiasts. The larger the film, the greater the resolution, of course. All worked with mechanisms similar to common 16mm projectors. I'll examine this Bell & Howell 1580 16mm projector built in 1979. We'll look at the shuttle that starts and stops the film, the shutter that strategically blocks light, and the photosensor that reads the sound, all of which operate in harmony. To create the illusion of movement, a series of still images, the film, is pulled off the supply reel, threaded in between the lamp and lens so the image can be projected, then run across the sound drum, and finally coiled onto the take-up reel. However, it isn't as simple as that sounds. To see why, here's what happens if you just move the film continuously past the projector's lamp. What you see is a blur. You can just make out the images. Here's what really happens shown in slow motion. A frame appears on the screen, not moving, then the screen goes blank, and then the next frame is projected on the screen. The projector must hold the image on the screen for a moment and then cover up the image while the film moves to the next frame. Two mechanisms do this. First, the shuttle. The shuttle has 3 teeth which engage the sprocket holes in the film. The shuttle moves back to disengage from the film, then moves up, then forward to engage the film, then moves down, pulling the film with it. The film is stationary most of the time and only moves when the shuttle is moving down. This is the intermittent motion of the film necessary to avoid blurring of the projected image. Here is slow motion footage of the shuttle moving up and down intermittently. From this angle, you clearly see the shuttle move forward and back to engage and disengage from the film. 2 shuttle arms hold the teeth of the shuttle in place. In between the arms is an eccentric cam. This cam rotates with an axle and moves the shuttle arms up and down. The outline of the cam has a constant width so that the distance between the arms doesn't change. The cam shape holds the shuttle steady at the top and bottom of its travel. To see how the shuttle moves forward and backward, let's look down from above. The shuttle arms act like a third-class lever. They pivot on one end, and at the other end, a spring force pushes them forward and an effort forces them backwards. This backwards effort is created by a disc tilted a few degrees off of the axle. When the axle turns, the disc wobbles. A horizontal post connected to the shuttle arms is pressed into contact with the wobbling disc by the spring force. As the axle turns and the disc wobbles, the shuttle arms are rhythmically pressed backwards. This movement is synced with the eccentric cam to create the required motion of the shuttle. The shuttle transports the film so that it's stationary most of the time and quickly advances to the next frame. Though it is rapid, the film movement will still cause blur in the projected image. The blur is eliminated by a shutter. The shutter is a disc with a blade that protrudes from half the circumference. The other half is open. The shutter rotates once every frame and is synced so that the shutter blade blocks light from the lamp while the shuttle is advancing the film. This prevents the projection of film motion on the screen. The film passes by the lamp at 24 frames per second. At that rate, the human mind blends the still frames into fluid motion. A projector with a single bladed shutter blocks light from the lamp once every frame. So half the time, every 24th of a second, the screen is dark. This switching between a bright projected image and darkness is called flicker. If the flicker occurs at about 60 to 70 times per second, the bright flashes fuse together and appear, to the human eye, continuously bright with no periods of darkness. This rate is called the flicker fusion threshold. Since 24 flickers per second is below the threshold, the flicker is visible. This flicker is the origin of the term flick as slang for movies. But modern film projectors don't have this problem. How did they fix it? Originally, shutters had a single blade that covered the advancement of the film with an open section that showed the picture. Modern shutters have 3 blades. The first blade covers the film motion. The second 2 blades block the light even when the film is stationary. They only serve to increase the flicker rate. The 3 openings allow the image to be projected half the time. Here I've labeled the 3 blades with 1, 2, and 3 dots. Notice that the shuttle moves downward only when blade number 1 blocks the light. The 3-bladed shutter is a simple and inexpensive solution that works well. The frame rate stays at 24 frames per second, and the flicker rate increases to 72 flickers per second, above the flicker fusion threshold, so the movie appears to move smoothly and without distracting flicker. This means if you watch a film in slow motion, you will see a single frame is flashed on the screen 3 times before the next frame appears. A subtle but important detail of film projectors is the film loop. The loop allows for 2 kinds of motion of the film, intermittent and continuous. The key is they happen simultaneously. The film must pause in front of the lens to project without blur, but must also move continuously for the proper playback of the sound. The top sprocket pulls the film from the supply reel continuously. A loop of slack film starts to form. This slack allows the shuttle to quickly advance to the next frame without tearing the film. A second loop of slack film at the bottom also forms. The bottom sprocket pulls the film continuously. This is important because it allows the sound to be read correctly. Sound in movies is recorded optically on the edge of the film. After the film runs past the lamp, it runs across the sound drum. To read this optical soundtrack, light shines through a tube with a slit. This concentrates the light on a small section of the film soundtrack. A photosensor on the other side of the film measures the amount of light passing through the film at a given time. The photosensor converts the amount of light transmitted into current, and this current drives the speakers. A soundtrack that oscillates slowly produces low-frequency sounds. If it oscillates more rapidly, it will produce higher frequencies. The volume is determined by the amplitude or width of the soundtrack. Louder sections are wide, and quieter sections are thinner. Because the image is projected here, and the sound is read down here, the soundtrack is offset 26 frames ahead of the picture in 16mm films. This offset ensures that the picture and sound are correctly synced. To me, the most beautiful aspect of the film projector is how all the mechanisms are synced. The mechanisms are driven by a single rotating axle. The axle rotates the shutter and simultaneously turns the cam and advances the film. Behind the shuttle is a worm screw that drives 2 gears that are coaxial with the top and bottom sprockets. So this means that with every rotation of the axle, the shutter blocks and flashes light 3 times. The shuttle pulls down a single frame, and the worm screw rotates the gears and sprockets 1/14 of revolution. Since there are 14 teeth on a sprocket, the top sprocket moves 1 frame worth of film from the supply reel, and the bottom sprocket pulls 1 frame through the projector. This setup keeps all the important mechanisms in sync. One thing to keep in mind is that film projectors were designed and built in parallel with film cameras. In fact, in many respects, the technology in both cameras and projectors are nearly identical. I'm Bill Hammack, the Engineer Guy.
For use as part of a talking picture, the sound to accompany the photographed action must be recorded for reproduction when the picture is shown. The most desirable material for this purpose has been found to be the photographic film. The finished film employed for reproduction in the motion picture theater, therefore, carries not only the picture of the action that is to be seen, as it did in the silent picture days, but also the photographic record of the sound that is to be. The sound and picture are usually photographed on separate films, which are called negatives. These negatives are combined by ordinary photographic printing to produce the positive print which is used in the theater to reproduce the original picture and sound. Since the photographic film is affected only by light, it is necessary for the recording of sound to convert the sound waves to corresponding changes in light. As I speak, the sound waves produced by my voice are transmitted through the air to the microphone, where these sound waves are converted to changes in an electric current. These variations in the electric current are then amplified and used to control the light falling on the photographic film. The light that falls upon the photographic film is in the form of a fine, bright line extending transversely of the direction in which the film moves. The part of the film on which the line of light falls to make the photographic sound record is called the sound track. When the line of light is so placed as normally to extend part way across the sound track, and the sound-controlled variations cause the position of one end of the line to move transversely of the track, a record known as a unilateral variable area soundtrack is produced. When both ends of the line of light are caused to move transversely of the track, a record known as a bilateral variable area soundtrack is produced. When the line of light extends completely across the soundtrack, and the thickness of the line is varied by the sound-controlled current variations, a record known as a variable density soundtrack is produced. All of these sound records contain photographic records of light variations corresponding to the pressure variations in the original sound. If either a variable area or a variable density sound record is run past a narrow line of light from a fixed source, and the light, after passing through the film, is visually observed, the amount of light reaching the observer is constantly varying from instant to instant. If the eye were capable of quantitatively measuring the light, it would see that the amount of light reaching it from either sound record varies in exactly the same way. There are in common use today electrical devices which will quantitatively measure what the eye can only approximate. The photoelectric cell is one such device and is universally used in the reproduction of photographic sound records. The reproducer system to which you are now listening contains such a photoelectric cell. This varying beam of light falling on the photoelectric cell produces variations in the electric current which are directly proportional to the variations in the light beam. As the varying electrical current in the photoelectric cell is small, a vacuum tube amplifier is required to increase it to the point where it will operate a loudspeaker. The loudspeaker converts the varying electrical current into sound waves, which are the counterpart of the sound waves falling on the microphone in the recording studio. To review, in the recording process, the original sound waves are converted to varying electrical current. The varying electrical current is converted to variations in a light beam, and the varying light beam produces a photographic sound record. In the reproducing process, the photographic sound record is used to produce a varying beam of light. The varying beam is converted into varying electrical current, and the varying electrical current is then converted back into sound waves. Since the advent of successful talking pictures in the late 20s, nearly all variable density photographic sound recording has been done by means of a device known as the light valve. The light valve contains two very thin metallic ribbons, tightly stretched and spaced very close together to form a light-transmitting slot. These ribbons lie in a strong magnetic field, and the amplified sound current flows through the ribbons. The electric current reacts with the magnetic field, causing the ribbons to move like shutters, displacing them in direct proportion to the amplitude of the current. In order to ensure high-quality sound recording, the vibrating length of these thin ribbons is limited by bridges, over which the ribbons are tightly stretched. The tension of the ribbons is adjusted by tensioning means. The ribbons are so delicate and their separation and movements so slight that the action of the ribbons can be observed only with the aid of a microscope. The separation between the ribbons is actually less than a hair's breadth. A steady light, concentrated by a lens, passes through apertures in the magnetic pole pieces. This light is varied by the slot defined by the ribbons and is concentrated by another lens system to form a very fine line of light on the photographic film. Since the ribbons act as light-controlling shutters, any change in the sound current flowing through the ribbons will cause a corresponding change in the size of the light-transmitting slot, defined by their closely spaced edges, and therefore in the amount of light falling on the film. The device thus acts like a valve controlled by the sound current for controlling light. In the explanation of the light valve action that follows, attention will be directed particularly to the portions of the ribbons that control the light, and these portions and their movements will be shown schematically. In this schematic representation, it will be understood that the relative dimensions of the ribbons and the arrangement of their physical supports are illustrative rather than actual dimensions and arrangements. As has been explained, the ribbons lie in a magnetic field, and the amplified sound current flows through the ribbons. The electric current reacts with the magnetic field, causing the ribbons to move like shutters, displacing them in direct proportion to the amplitude of the current. A steady light is concentrated on the ribbons, and these ribbons, acting as shutters, cause variations in the light corresponding to the pressure variations in the original sound. This varying light causes variation in the exposure of the film. The exposed film, when developed and printed, is the sound record. The soundtrack used for the reproduction of music will be shown on the screen, and the soundtrack will be changed from a variable area to a variable density track simultaneously on both the picture and sound record. The photoelectric cell and the entire reproducing system is the same in all cases.
Hey YouTube, I'm Nick from Nick28TK, and this is Optically Stored Audio.
Hey guys, for this week's project I'm going to try and store that little snippet of sound you just heard transmitted by my oscilloscope and picked up by this light to sound converter, and I'm going to try and store it on regular film. The original technique for storing audio on optical tape was invented in 1922 by Charles Hoxsey, and it was called the Photophone. It worked by shining a light onto a vibrating mirror. That light was then reflected onto moving tape, and that would record the shape of the waveform of the sound that was modulating the light. When this was pulled past a photocell, the changing light and dark patterns on the film would reproduce the sound when the photocell was hooked to a speaker. I'm intending to do this using an old 35mm stills camera, where I'll wind all the film through as if it was finished, but I won't expose any of it. I'm then going to play back a sound using the dot on my oscilloscope. The dot will move up and down, and as it's moving, I'll start winding all that film backwards into the canister. And if I do it at just the right speed, it'll store the movement of that dot as the film moves past. I'll be able to put it in front of my own photo sensor that turns light into sound, and hopefully I'll be able to hear the sound that I played into the dot on the oscilloscope. I've only got one shot at this, so I'm going to lock the shutter open, press play, start winding, and hope everything works as expected. The shutter is now open.
Hey YouTube, I'm Nick from Nick282K, and this is optically stored audio.
And that was it. It only takes about 15 minutes to develop color film by hand. After another hour or so of drying, these are the results. This is my playback device for my audio film. If you look closely here at the film, you can see the audio track in it. And that audio track passes in front of one of these two little slits, and the light passing through the slit and through the film falls onto that little LED that I'm using as a photo detector. As I pull the film through, we should be able to hear my voice playing through these speakers. I'm going to set the camera up on the tripod, and we'll see if we can hear anything. Using the halogen light didn't work too well. I suspect there's a lot of electrical noise. Even though the filament has a lot of thermal mass, there's still quite a loud hum coming from the line. So I've switched to an LED flashlight that runs on batteries, which means it's going to have a lot steadier light output. And I'm going to hook the amplifier board here right up to the camera, so maybe we'll get a little bit clearer audio from it. So the results are not too bad. I think the biggest problem is actually my playback setup. When you look at the film up close, there's a lot of detail in that trace, just as much as if you were to look at the waveform on the computer.
Ever think what a sound looks like? An artist might picture it this way. But a musician sees it differently. The sound engineer has an oscilloscope to help him see sounds. Let's have a few notes on the guitar. And there's another way these notes can be seen. The vibrating strings set up vibrations in the air, which travel to the microphone. And then an electronic device translates them into vibrations of light. This narrow beam of light is photographed on movie film and gives you the soundtrack, which doesn't appear on the screen. But let's bring it out of hiding where we can see it. Come on. All right, now, give us that guitar again. So that's a picture of the guitar notes. Well, can you show us some other instrument? Uh-huh. What else can you do? Not bad. Try again. You know, that's a mighty fine-looking voice. Wonder what you could do with my voice. Shall we try it? This is my voice. Wait a minute. Let's hold that still and look at it again. So that's how my voice looks. Like every other sound, it has its own distinct pattern of light and dark running down the side of the film. Well, if a sound will make a pattern on film, a pattern on film will make a sound. You can even create your own sounds by drawing directly on the film. Norman McLaren, the motion picture artist, has been making some hand-drawn sounds, and now he's going to hear them for the first time, played on the Moviola, a sort of miniature movie projector. It's not just guesswork. The sound of any of these patterns of lines can be calculated. The size controls the loudness. A row of small marks would sound like this. Larger marks, a louder sound. That's simple enough. Then there's the tone quality. It's controlled by the shape of the marks. This series of thin, straight lines gives a sharp, rather unpleasant sound. But these round dots are a bit smoother. The marks can be any shape you like. Now, how about this? Using the brush, Norman tries a row of small triangles. These sharp, angular forms, what would they sound like? The distance the lines are apart controls pitch. With the lines far apart, a low-pitched note, a medium, and a high note. Now, what can they be used for, these hand-drawn sounds? Well, Norman McLaren finds that they are a perfectly natural accompaniment to some of his hand-drawn motion pictures. Each movement of the screen can have its own specially designed sound. Making movies this way, the artist has direct personal control at every stage of the film's production. Sound and picture are planned and closely related to each other as they are drawn. Now Norman is checking to make sure that each bit of sound is perfectly matched to its accompanying screen action. Finally, the picture and the sound will be printed together on one length of film, and color will be added during the process.